Okay. So, is it? Do you see any indication that it is recording?
Yes.
Yes. Okay. Very good. So let us begin. So we're going to start by talking about special relativity or physics in flat space-time. So just even before we start, two things. One, do you have any questions from the last meeting that we have? I wouldn't expect it would be too much because we haven't really started. And the second is we're basically supposed to have today a 1 hour lecture and 1 hour tutorial. Since there is no designated tutor, then generally I just simply mix. And since we haven't had things to tutor yet, then we're going to have a double lecture. So we use the time for lecture, and in other times we might use the time slot for tutorial. We see, I'm keeping kind of, how to say, flexible based on how we are making progress. Okay. So, by the way, I asked you last time to refresh your memory about special relativity. Go to what you learned in the first year, special relativity. How many of you have actually done that? See, a few did. Okay, very good. So we're going to do special relativity now. The purpose is, one, to refresh your memory, but more importantly, to introduce the concepts of vectors and tensors, and we'll start working with them. So you start learning a language. Now, I would say special relativity is based on the principle of relativity, right? And the principle of relativity, which we stated previously, says that the laws of nature are invariant in all inertial reference frames. Okay, so let me write it down. The laws of nature are invariant in all inertial reference frames. Yoo-hoo. The technology actually made it possible to get this out of the way. If you have any clue, how do I get this out of the way? Get out. Nope. Okay. No clue how I get this out of the way. I just have to live with that for the time being. Okay, so this is the principle of special relativity, and that's it's the experimental basis is of course the Michelson and Morley experiment. Oh, that annoys me. I want to get this out. No, it's not this one. Get this out.
אסף, אני חושבת שאתה יכול ללחוץ על הלוגו הכי ימני למעלה, ואולי זה יעזור. שנראה כמו מחברת.
Yeah, it does. Thank you. Thank you very much. Okay. So the experimental basis, as we said, well, let's write it down. So this is the principle of relativity. And the experimental basis, of course, is the experiment by Michelson and Morley. which shows that the speed of light is constant and equal to c in every inertial frame. So Michelson-Morley. Experimental basis. The speed of light is constant. So in every inertial frame. Okay, very good. So this, of course, is in contradiction to the Galilean transformation, right? So we have two observers, one in reference frame O, one in reference frame O prime. And so we have one O and another one O prime. The O prime is moving with respect to O at some speed u, and both of them are observing some object, green object, which is moving at some velocity v, as seen by observer O, and v prime as seen by observer O prime. And Galileo told us that v prime is just v plus u, and of course we know this is no longer true. Okay, instead, what Michelson and Morley told us is that let's again look at these two observers. So we have an observer O. Let's say that we have an observer O. And let's have an observer O prime. Which is moving at some constant velocity with respect to O. Now, any observer denotes any event, and this is something which is quite useful for you to remember from the start. In relativity, it's easiest to think in terms of events. So any observer denotes an event for coordinates, right? The time. Event is denoted by time and place, right? Time, X, Y, and Z, as seen by observer O. And as seen by observer O prime, in his or her frame, it will be T prime, X prime, Y prime, and Z prime, right? This is the first thing to remember to not get confused. Relativity can be extremely confusing. So the thing to remember is that we always speak about events in special relativity, okay? Somebody scored a goal, that's an event. It happened at a certain place at a certain time. Two people kissed, that's an event. A particle decayed into two particles, that's an event, okay? Every observer, right, can look at the system and state the time and place that each event took place. Okay, an event occurred at time t and at location r, right? Vector r, which is x, y, and z. Okay, fine, good. Now, now we said that observer O prime is moving with respect to observer O at some velocity, let's say v or u. Let's say again that without loss of generality, at time t equal to t prime equal to 0, they both had the same origin. So let's say at t equal t prime equal to 0, then the coordinate origin of coordinates O prime coincide. Okay, otherwise, it's a simple translation of origin of coordinates, right? Now, let's go back to Michelson and Morley. And let's say that there was a light source that is located at the origin. So there is a flashlight here. Right, or here, right, t equal to 0. Right, so at time t equal to 0, when space equal to 0, photon or crescent of light was emitted. Right, now at time t, right, the spherical wave front of the light is at location, which is given by at time t equal to 0, x equal to 0, light was emitted. So from observer O, right, at some time t later, the front of the, the spherical wave of the light would be at some location, x, y, and z, which is given by the front of the light as seen by O at time t is at location x squared plus y squared plus z squared, which is equal to c squared t squared. Right? Light travels at the speed of light. Okay? I didn't say anything surprising. What about observer O prime? What would she say? Again, her origin of coordinate coincides with the origin of coordinate O, right? At t equal to 0. That's when the light was emitted. So after some time t prime in her frame, when would be the presence of light at the front of the light wave? It's not a tricky question, guys.
The same, but with t prime in our coordinate.
Exactly, right? So she will say for observer O prime, right, it will be x prime squared plus y prime squared plus z prime squared is equal to c squared t prime squared. This is exactly what Michelson and Morley said, right? Regardless of the motion of the observer, the light always travels at the speed of light. One thing. The second point, do not mix coordinates. The coordinates without the primes, the ones that I wrote in blue, t, x, y, and z, this is what the observer, the blue observer, has. The coordinates t prime, x prime, y prime, z prime is what the red observer, O prime observer use. Okay? Do not make the mistake. Sometimes people, especially at the beginning, make the mistake and starts having primed and unprimed coordinates in the same equation. That's really meaningless, generally. Don't do that. The correct way of thinking, there is an observer. I'm observing the system. I define my own coordinates. I have a full right to do that. Now you're observing a system. It's the same system, but you define your own coordinates and you have the full right to do that. Your coordinates do not have to be the same as my coordinates. Generally, they would not be the same. Okay, but if you want to talk to each other, I want to tell you, hey, I saw something really interesting happening there, right? I need to be able to give you the message of what do I mean by there, right? That's it. So this is the Michelson and Morley. Now, of course, we can assume without loss of generality, as I showed here, that, O prime moves in the X direction relative to O. It doesn't have to be. So of course, generally, what we have is that X prime is not the same as X, but Y prime is the same as Y, and Z prime is the same as Z. So without loss of generality, assume that O prime moves with respect to O in the X direction. Because we have that X prime is not the same as X, Y prime is the same as Y, and Z prime is the same as Z. Generally, right? So obviously from these two equations, we end up that T prime must not be the same as T. Cannot be the same, right? So time separation is not the same in both frames, right? So in what we say is that time is not an invariant quantity, right? So two observers that observe some event or time difference between two events. What I really measure here is the time difference. There was the first event was that the photon was emitted, and the second event was that the photon was observed. So I'm measuring the time difference between these two events, right? And this is not a conserved quantity. This is not an invariant quantity. So we say that time is not an invariant quantity. Right? So far, so good. But, right, the time separation is not an invariant quantity. But can you think of an invariant quantity? Can you think of a quantity that is invariant, namely that both observers would agree on that quantity?
The interval between two events?
Exactly, very good. So there is a quantity which is called the interval, an invariant quantity. Is the interval, right, between two events. And I define the interval, define the interval squared. Just delta S squared, which the definition is minus C delta T squared plus delta R squared, or minus C squared delta T squared plus delta X squared plus delta Y squared plus delta Z squared. Okay, pay careful attention. I'm talking about difference between two quantities, two events, sorry, right? The first event occurred at time T1 and spatial location X1, X2, X1, Y1, and Z1. And the second event occurred at time T2 and spatial locations X2, Y2, and Z2. Right, the difference between them, right, delta Z, Z2 minus Z1, delta X, X2 minus X1, etc. For each observer, they will occur at a different location in space and a different time. But both observers, when they will compare the interval between the two events that happen, they will agree. They'll get the same result. Okay, that's clear? Now, there is a very close analogy between this concept of an interval and the concept of a distance, which you're familiar with from Euclidean mechanics or Euclidean geometry, sorry, not mechanics, right? So analogy, right, is the concept of the distance. In 2D or 3D or ND, doesn't matter, Euclidean space. Right. So I have a 2D space here, right? So I define two coordinates, X and Y, right? And I can define 2 points, right? That point has coordinates X1 and Y1. That point has coordinates X2 and Y2. And what's the distance between the points? What is that?
The difference, of course, x2 minus x1 squared, etc.
Y2 minus Y1 squared plus X2 minus X1 squared, right? Now let's say that there is a different observer whose coordinate frame is rotated relative to me. Right? I had some beers. I'm looking like that a little bit. So I'm now looking at the space a little bit tilted, right? So right now, with the new observer, right? The location of each point, right? It says this point here has coordinate x1 prime and y1 prime. And this coordinate here is, this point here has coordinates x2 prime and y2 prime, right? And of course, in general, x1 prime is different than x1, and y1 prime is different than y1, and the same x2 prime and y2 prime are not the same as x2 and y2. But the distance squared, delta s prime squared, is delta s squared, right? Both observers would disagree on the coordinate of each individual point, but they would agree that the distance between these 2 points, they agree on the value of the distance, right? Right? So we say that the distance is invariant under rotation of the coordinate system. Fine? Cool? Good.
Can you please repeat what can you please go back just a bit for the interval and explain it again?
Yeah, I defined an interval as a quantity which is invariant. The interval is defined here. The interval squared is minus c delta t squared plus delta r squared, right? Plus delta x squared, plus delta y squared, plus delta z squared. Again, delta x is the spatial difference between 2 events. I'm looking at events. Any event took place at a certain time, at a certain place. And as we said, two observers will disagree, will not necessarily agree on the location in which each event took place, and will not agree necessarily on the time in which each event took place, but they will agree on the interval. The interval between two events.
So if you say if in the analogy for two-dimensional or three-dimensional Euclidean space is distance, then you say that if I and someone else look at the same event from different points of view, we would say that even though the time it takes for the event to occur is different, and the places where it takes, the distance that it passes will be the same for both of us.
No. Good that you asked that. Interval is defined between two events.
Mm-hmm.
Between two events. Okay? Event occurs at a certain point at a certain time. A particle decayed. That is an event. Two people kissed. That is an event. Think in terms of events. Now I'm talking about the interval between two events. Two events are separated by distance. They are separated by time. They don't occur necessarily at the same location. They don't occur necessarily at the same time. Okay? Now, and I'm seeing events. I will associate to the event a location, a spatial location, and a time. You will associate to the same event a different time and a different space, a different location. Who's right? We're both right. There's no right or wrong here.
So basically if my point of view has a different time and location than your point of view, the way that they will change one another will be such as that the interval will stay the same.
The way that what will happen is that the interval between two events, that's important. I'm seeing one event, I associated it to its time and space. I see a second event, I associate to it another time and another space. Now you're seeing these two events. To each one, you associate your own separate time and space, which are different than mine. But when we say, oh, can you tell me what is the interval between these two events? We will get to the same answer. That is what Michelson and Morley told us.
I see. Okay, thank you.
Okay. Now, we can start speaking about transformation between my system and your system so that we can talk to each other. How do we call a transformation between one coordinate system to the other?
Lorentz
transformation, right? So, Lorentz transformation. Right. So the interval that we just introduced connects space and time, right, into one four-dimensional space-time. How do we call this four-dimensional space-time?
Minkowski.
Minkowski, very good. So the interval connects space and time into 4D space-time known as Minkowski space. Okay. So in the Minkowski space, again, we define an event by four coordinates: time, x, y, and z. So we must have four quantities to define an event in this space. Now, of course, we can use time, x, y, and z. but it's not going to be, we can do that. But of course, we want to confuse you and to make things calculations much faster. So at any event, we're going to define by a 4 vector of coordinates. So any event in Minkowski space is defined by a 4 vector of coordinates. Which we denoted with x mu. Careful, mu is an upper index. It's not, x mu is not x mu. Careful. X mu with a Greek letter upper index, that's the standard, which is simply x0 is ct, x1 is x, x2 is y, and x3 is z. Now, in very, very, very old textbooks, the time component is denoted by x4, but we don't see that anymore, so forget about it. Just a comment in case you're really interested in going to the library and reading old textbooks. Okay, so this 4 vector of coordinates x mu, again upper index, can be any Greek letter that you put there. It's just a convention that people normally use. That fully specify the space-time location of each event. Okay. Now, if we need to refer to only the space part, but not to the temporal part, this is something which we will do when we discuss cosmology. Then rather than Greek letter, we will describe it with a Latin letter. So if we need to refer only to the space or spatial space coordinate, we use Latin superscripts. Right. So xi, right? x1 is x, x2 is y, and x3 is z. The only place in the course, I think, if I remember properly, that we use that is in the cosmology part. Normally, we're using the 4 vectors and we denote them with Greek letters. It can be x mu, it can be x alpha, it can be x rho, it can be many letters. Most frequently you'd find in literature would be mu and nu. Nu or ni, I'm always confused. Get used to it. That's a very good opportunity to refresh your Greek knowledge because we're going to use a lot of Greek letters here. Okay. Now, before we're going to proceed, I'm going to introduce a new notation that is going to write the interval in a more compact form. For that, I'm going to introduce a matrix. It's a 4x4 matrix. So we now introduce a 4x4 matrix. It's a very special and important matrix. It has a special name. It's called the metric. And we're going to write this matrix using 2 lower indices. So we denote it with an eta. the Greek letter eta, and it has two lower indices, mu and nu. And it's actually a very simple matrix. It's mainly zeros, except from the diagonal. And the diagonal is having a -1, and then a +1, +1, and +1. Simple matrix. Just, again, as a reference, people doing particle physics, they also use this matrix, but they use it with the opposite notation. So it's a +1, minus, minus, minus. Just say eta nu particles is a -1 times eta mu astro, gr, whatever. Just that you know that. I could find two reasons for that. The main one, of course, is to confuse the poor students. And the second one is to ensure that when particle physics is talked to their astrophysics colleagues, then they confuse each other. There is no other good reason for that. Now, this is a course in GR, so we're going to stick to this notation. This is the notation that you're going to find in all GR textbooks. If you're going to study particle physics, you'll find the opposite notation in their textbooks. Okay. Now, with this new and compact form, I can write down this interval, which I introduced here. I think I can do a trick. There's some sort of trick here. Yeah. If I do something like that. Right. Copy. Now I can take it and do here and paste. It actually work. So using that, I can now write the interval in a much more compact form. I can write down the interval delta S squared S sum over mu and nu, which go from 0 to 3, of eta mu nu times delta x nu times delta x nu. Now, do you see that this equation that I just wrote is the same as the interval that I wrote previously? No, you don't see that? Well, let's see. What happens if mu is different than nu? What do we get? So how many terms do we have here? How many terms are we summing over?
16.
16, right? We have 16 terms because we're summing over mu and nu. They go from 0 to 3, so there are 4 times 4. We have total of 16. But look at this matrix eta, right? If mu is different than nu, then the matrix eta gives us automatically 0. So 12 out of the 16 are 0. Now, if mu and nu are equal to 0, 0, so eta 0, 0 is what? What is eta 0, 0?
-1.
It's a -1. If you want to say something, make sure that your microphone is open so I can hear you. All right, it's a -1 times delta x 0, delta x 0. What is delta x 0?
CT, yeah.
C delta t. Right, delta x is C delta t. So I have here a minus. Right, I have here a minus C squared delta T squared. If mu and nu are equal to 1 each, then what do we get?
1.
Delta x squared.
1 times delta
1
x
delta x.
squared. So what is written here is identical to what is written here. Right? Easy, huh? Okay.
Saf,
Yes.
a question about the notations.
Yeah.
You have to sum in this way.
Yeah.
Lower eta mu nu and then upper x mu and x nu.
Correct.
I mean, you can just change the indices. I mean, it has to be that way.
Wait. It's a very good question. Give me a few more minutes and I'll clarify things. Okay. So directly related to your question, we have here summation over indexes, right? And we have here one upper index and one lower index, which we are summing over. So it is understood that every time we have an equation where there is an upper index and a lower index on the same side of the equation, we are summing over them. That's called Einstein's summation convention. Thank Einstein for that. So we can simply write it as eta mu nu delta x mu delta x nu. There is no need to put the summation sign because it's understood that every time you're seeing an equation which have the same index, right? Mu or nu, which appears once in an upper index and one as a lower index on the same side of the equation, we're simply summing over them. So you're going to see a lot of these type of equations. If you find it confusing, then very easily, simply add up a summation. Every time you're seeing an index that appears once as an upper index, once as a lower index. So we're not going to use that because that's called Einstein summation convention. Okay. Now, also related to your question, since we are summing over these indices, right, then really these are called as dummy indices. So rather than mu or nu, you can put any other Greek letter, it doesn't matter, because we simply sum over it. And it sums from 0 to 3, 0, 1 to 3. So I could write here a rho and a sigma, alpha and a delta, it doesn't matter. That's called dummy indices. Okay, any index that appears twice on the same side of the equation once as upper and once as lower is a dummy index. And is being summed. If you see that the same index appears twice on the same side of the equation, both as an upper, both times upper or both times lower, you know you did something wrong. This cannot be.
Can I ask another question?
Yes.
And in all, for the rest of our course, no matter what, we will always sum the indexes from 0 to 3 because we'll talk about 4D space-time?
Yes.
Okay.
Unless it's a Latin index and then it's only the space part.
Okay.
1, 2, 3. Okay, more? No. Now we can define a Lorentz transformation. So what is a Lorentz transformation? Help me.
A transformation that keeps the interval unchanged.
Excellent. Very good. Am I going too slow? By the way, I can speed up. I see that people are good. Should I go faster? Some say no, but some I think say yes, no? Okay. And most don't say anything. You can say. Does that a yes? I don't know. Okay. The Lorentz transformation right is defined as a transformation from one coordinate system to another that conserves the interval. So let's start. So the simplest example of such a transformation that's the definition of a Lorentz transformation. So one example of a Lorentz transformation.
It's from electric to magnetic field?
No.
Ah, no, okay.
Rotation?
About electric fields. Yeah, even simpler than that.
Time dilation?
What?
Time dilation?
No. I didn't say, look, you're using terms in physics. I'm using terms in math. You're speaking about time and fields, electric field, magnetic field. I'm talking about, coordinates, intervals. This got nothing to do with, there's no physics. I didn't put any physics here, except for Michelson and Morley experiment, of course. I'm talking about the generally mathematical structure that we have here. So the first one, simplest, is translation. Right? What is translation? It's just a shift of coordinates. So x mu goes to x mu prime, which is just x mu plus a mu. Right? That's a translation. It includes shift in time and includes shift in space of the origin. Right? Good. A mu, of course, is a number, right? Four fixed numbers. So just 4 fixed numbers. Yeah, just a small note about notation. I put x mu prime and not x prime mu, right? Because x2 is y. So if I want to say y prime, I said x2 prime. So that's the reason. That's why I put the prime here, right? And x mu prime. So just about notation. Of course, the translation leaves the difference between the coordinates of each event unchanged, right? So delta x mu is unchanged, and so it's a legitimate Lorentz transformation because the interval is unchanged. So it's just a simple shift of the origin. The only other kind is a rotation, right? Right, or any other kind of a linear transformation. Is to take the 4 vector and multiply it by some matrix. So only other kind, right, is to take x mu prime and write it again. Pay careful attention to how I'm going to write it. Lambda mu prime, small space nu, x nu. Again, lambda nu prime, there is like a space here. Nu is after the nu prime. It's not below it. Again, this is not the same as this. This, one on top of the other, do not exist. I don't want to see that. This doesn't exist. Okay, we will get to that. Believe me, we will get to that. Okay, for in the meantime, just pay careful attention to how you write things. Have in mind this equation, right? I can write it down. Again, we have the summation. We have Einstein's summation here on the right-hand side of the equation. I can write it down as x mu prime is lambda mu prime 0 x 0 plus lambda mu prime 1 x 1 plus lambda mu prime 2 x 2 plus lambda mu prime 3 x 3. That's what's written here. You see that? Yeah? Okay. Now I can also write it as x prime is equal lambda x. I'm not going to do that because I don't want to confuse you too much. Now, so this is a general, lambda is a general 4x4 matrix, right? But it's not general, right? Because it has to fulfill a certain condition, which is to conserve the interval. So what conditions should the matrix lambda fulfill in order for it to be a legitimate Lorentz transformation, right? So in order to conserve the interval, what did we say about the interval? So let's say the prime guy, delta S prime squared. How can I write it?
The same as before, x mu at mu nu, x nu.
Only it's prime now, right? So delta S prime squared, it's the interval is viewed in the prime frame. Again, don't confuse prime and unprime. This is not something legal because you're confusing two different point of views. But X prime guy or girl, the interval is eta mu prime, delta X mu prime, delta X nu prime. Right? Now, but now I can use the Lorentz transformation between the different coordinates of the interval, right? Which is written here. So I can write it down as eta mu prime, and then delta X mu prime. I'll write this lambda mu prime, then pick up your favorite Greek letter, call it rho, delta X rho. And then the same for nu prime. So delta x nu prime, I'll write as lambda nu prime sigma, delta x sigma again. It's just a dummy. If you choose alpha, you can choose any other letter here, but it's not primed. Because now I'm moving to the other observer, right? The original observer. And so this needs to be equal. I want it to be equal to the interval as seen by the first observer. That's why I put the man kriya, whatever how you call it. So it's going to be eta rho sigma delta x rho delta x sigma, which is just delta s squared. Again, if things get confuse you, remember we have a lot of summations here. Plenty of summations. We're summing over what here?
Nu prime and nu prime.
Nu prime, right? What else?
And rho.
And rho and
Sigma.
sigma. There's plenty of summations around here. You don't see it because I don't write it. But you have to look at it and then you can see it right away.
The subscript for the matrix lambda is on the diagonal?
What do you mean by diagonal?
For example, if I look at eta, then I can say that each of the subscripts tells me a position on the matrix 0, 0, 0, 1, and such and such. But on lambda, there's only one subscript, right?
Right there, one subscript and one superscript.
Yes. So yes. So the superscript would mean what? So the superscript.
Yeah, it will mean the rows and the columns. Well, we'll get to that in a few minutes.
Okay.
Okay. The most important thing to remember is not to get confused with the indexes. Put them in the right place, as a superscript or as a subscript. Do not mix them, because then you get lost and you get nowhere. Okay. Now, so we want the interval to be conserved, right? So in order for the interval to be conserved, now what we do here, since we have all this summation, it really means we're going term by term, which means that since we're going term by term, I can just take this term here, right, and then just move it over here, because we're really summing, right? It's all about terms here. So we end up, right, that this equation will be fulfilled if eta rho sigma is equal to lambda mu prime rho lambda mu prime sigma eta mu prime mu prime. So every matrix lambda whose elements fulfill this equations is a Lorentz transformation. How many equations did I just write right now? How many equations do you see here? How many equations are written here?
Rho times sigma.
What is rho times sigma? Give me a number.
16.
16 equations are written here. Because rho and sigma, each one can go from 0 to 3, 0, 1 to 3. There are 16 equations. how many terms in the right-hand side of each equation?
Also 16.
Also 16. Why 16?
Because each of the indexes go from 0 to 3. We have two of
Okay,
them.
because there is a summation here. There is a summation here over mu prime and u prime, which go from 0 to 3. So we have a total of 16 equations. Each one has 16 terms. And matrix that fulfill all these equations is a Lorentz transformation. Now that sounds a lot, but remember the eta matrix is very helpful because unless mu is equal to nu, or mu prime equal to nu prime, or rho is equal to sigma, it's going to give us 0. So out of all these 256 terms here, most of them are going to turn out to be zeros, which saves us a lot of computational time. If you want to give it to the computer, this is what you tell the computer to calculate. Right? Somehow the faces are not so happy anymore. We haven't even started, guys. It's okay, you're learning a new language. Okay, so any matrix which satisfies this is a Lorentz transformation. This is a Lorentz transformation. Now, the set of all Lorentz transformations form a group. This is called the Lorentz group. Again, it's very closely analog to the rotation group in 3D space. I'm not going to get into group theory here. There's no need. It's an abelian group. We'll get to that later. Maybe I'll get to that later. We'll see. There's no real need, actually. So we have several categories of Lorentz transformation. Categories. So the first category is just a rotation. Right. So for example, rotation in the XY plane. Right. So rotation in the XY plane. Right. XY plane. Lambda, u prime, nu. You know how it looks like. 1, 0, 0, 0, 0, 0, 0. Cosine theta, sine theta, 0 minus sine theta, cosine theta, 0, 0, 0, 1. That's a rotation matrix, right? Time x, y, z, x0, x1, x2, x3. Right. That's a rotation. That is a legitimate Lorentz transformation. Right? Of course, theta can take value between 0 and 2 pi. Yeah. You want us to check it? Let's check it out, right? So we have 16 equations, so let's choose one of them. For example, right? Let's take rho equal to 1 and sigma equal to 1. What is eta 1, 1?
-1. No, +1. Sorry.
+1, right? So we have a 1 equal eta 1, 1, which is lambda 1 mu prime rho is 1, lambda mu prime rho is 1, right? Eta mu prime mu prime. So we still have 16 terms here, but eta really helps us, right? Because we only must have things that mu is equal to mu prime is equal to nu prime. Otherwise, everything else is going to be 0, right? So the only non-zero terms, help me. What will be the non-zero terms from nu prime and nu prime?
1 cosine theta, and again.
Right. If mu prime is equal to 0, what do we get?
-1 after all.
-1, but what would be then in the contribution from the lambda matrix?
Cosine theta?
No, 0, right? 0 and 1, so it's this one. Right, 0, zero, 1, 2, 3, 0, 1, 2, 3, right? 0, 1, we're gonna get a 0. Come on, guys. Here I can use mu prime equal to nu prime, because otherwise, if it's not diagonal, we're gonna get a 0 anyway. So lambda 0, 1, lambda 0, 1, eta 0, 0, plus lambda 1, 1, lambda 1, 1, eta 1, 1, plus lambda 2, 1, lambda 2, 1, eta 2, 2, plus lambda 3, 1, lambda 3, 1, eta 3, 3. Now let's see. What is lambda 0, 1?
0.
0. So this, the first term is 0. Now, what is lambda 1, 1?
Cosine theta.
Cosine theta, we have it squared. So cosine theta squared. And what is eta 1, 1?
1.
1.
1 times plus 1. What is lambda 2, 1?
Minus sine theta. It
2
depends, or sine theta.
Sine theta, okay. So anyway, we square it, so it doesn't matter. Plus sine theta squared. And eta 2, 2 plus 1. What is lambda 3, 1?
0.
0, right? 3, 1. So 3, 1. So this one. 0, right? So we have plus a 0. So we end up with a cosine squared theta plus sine squared theta, which is indeed 1. Right? So we did one example, right? You can do all the 16. Try this at home. You can do all the 16 and you end up with you know, that all the terms fulfill this requirement that is written here, right? This requirement. And therefore this matrix represents a legitimate Lorentz transformation.
Yeah, but actually it's 16 equations in the abstract case, but you can just do matrix multiplication and you get everything very fast.
Whatever you want, but this is the definition. This is the mathematical definition of the Lorentz transformation. The notation is completely abstract. You can do it whatever you want, but this is essentially this is the definition of a Lorentz transformation here. Okay, so we have 16 such equations, and that's fine. Which is, as you can see from here, this is really identical to 3D rotation in Euclidean space, right? I didn't touch the time, I just did rotation in Euclidean space. Rotation in Euclidean space is a perfectly legitimate Lorentz transformation. Okay, the next transformation, we call it, you might know the name, it's called boost. So a boost, what is that? This is just a rotation, but when one of the coordinates is the time. That's the right way to think of it, right? So we have a rotation, but not just the two coordinates that we are rotating are both spatial coordinates, but one of them is the time coordinate. Right? So rotation between space and time direction. For example, right, rotation in the t and x. Write it down, lambda, mu prime mu. Since I'm using time now, what I'm going to do, rather than cosine and sine, I'm going to use cosine hyperbolicus and sine hyperbolicus because I have this extra minus sign. So I have a cosine hyperbolicus phi, and then there will be an extra minus sign. Minus sine hyperbolicus phi, 0, 0, and then minus sine hyperbolicus of phi, cosine hyperbolicus of phi, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1. So the format, as you can see, is the same as the format of a rotation. Just we changed from cosine and sine to cosine hyperbolicus and sinus hyperbolicus, and we added up one minus sign. Right. And of course, unlike the rotation angle, theta, which takes values between 0 and 2 pi, the boost parameter phi can take any value between minus infinity and plus infinity. Again, we can do a direct substitution. So check. Again, let's see, yeah, rho equal to 1, sigma equal to 1. One is eta 1, 1, right? Lambda mu prime 1, lambda mu prime 1, eta mu prime, mu prime. What will be the non-zero terms now? Come on, help me.
Again, mu prime need to be equal to nu prime for eta.
Yeah, that's true. And what values they can take? Which will be that values between 0 and 3. But what will be the non-zero values that they will get?
0 and 1 only.
0 and 1 only, exactly. So you have lambda 0, 1, lambda 0, 1, eta 0, 0, plus lambda 1, 1, lambda 1, 1, eta 1, 1. The rest are zeros. So what is lambda 0, 1, lambda 0, 1, eta 0, 0?
Sinus hyperbole, minus sinus hyperbole, right?
Yeah. That's it?
No, squared and minus 1 in the eta, from the eta.
Very good. And then?
Cosine hyperbole, the same manner.
Cosine hyperbolicus phi squared minus sine hyperbolicus phi squared, which is 1. Ta-da! Now we only did it for one component, but you have to actually check it for all the 16 components. And after you do it, you see that I was right, and this is indeed a legitimate Lorentz transformation. Now, of course, once we have Lorentz transformations, we can, put them one on top of the other. There is also the discrete transformation, which includes reversal of time, reversal of space. Right, now we can multiply individual transformations. We don't really need to do that. It's just going to make things messy and ugly. The only thing to note is that, you know, the set of transformation forms a group, but this is not, it's not commutative. It's not commutative, right? So this is called a non-abelian group. right? If you do, it's the same for rotations, right? Rotations are non-abelian, right? If you rotate first in the x around the x-axis and then around the y-axis, and then you take and rotate around the y-axis and then around the x-axis, you don't get the same result. You're all familiar with that, right? From your second year classical mechanics. Yeah, you know what I'm talking about. So I would say that the set of transformations is called form a group. Non-abelian group. Non-abelian.
I have a question regarding the group.
Yeah.
It should have like the identity and an additional 15 representation, right? 15 matrices which create the.
If you want to get the basis for the group, then yes.
But I know, but if I count them, you have like sphere rotation, right? Between the x, y, y, z, and x, z.
Yeah, you don't have 15. Sorry, you have much less, of course. You have 3 rotation. You have total of 10. You have rotations, and you have 4 boosts, and 3 boosts, and you have 4 translations. Yes, you have total of 10. Okay, so a total of 3 independent rotations, 3 independent boosts, and 4 independent translations. That's what you have. That's it. And if you combine the translations, then it's not the Lorentz group, it's called the Poincare group. Again, we don't really need that for the rest. So let's not get confused with group theory. Okay? Just that you know that it forms a group, it's called the Poincare group. Okay, questions more? No. Okay, now I know this looks, if this is the first time you're seeing it, it looks quite strange. Let's put it back to things that you've seen. You see that I'm not really tricking you. Let's take this equation, this Lorentz transformation, and put it in a form that you're familiar with. So let's apply this Lorentz transformation on a 4-vector x nu. So I'm going to take the Lorentz transformation here and apply it, lambda mu prime nu, apply it on x nu. Right, x nu, remember, right? X nu is just CT, x, y, z. The 4-vector. Right, so what is it equal to? So I take this transformation, right? This gives me CT prime. Just CT cosine hyperbolicus of phi minus x sine hyperbolicus of phi. Right, I take the matrix, multiply it by a vector, I get another vector. And x prime, what is it going to be equal to? What is it going to be equal to? This is the matrix.
Minus sine hyperbolic CT
Very
plus
good.
cosine.
Very good. So it's minus sine hyperbolicus of phi times CT plus x cosine hyperbolicus of phi. Yeah? You know how to multiply a matrix with a vector, right? I know you do. Okay, so if we look at the x prime equal to 0, right, the velocity, right, v, well, let's normalize it. Beta is the normalized velocity. It's V over C. So I'm using x prime equal to 0. What is that? It's just x over CT. So it just sine hyperbolic to phi divided by cosine hyperbolic to phi. So this is just tangent hyperbolic to phi. Now it's just a matter of some algebra and refresh your memory about hyperbolical functions. So we can write down 1 minus tangent hyperbolic to phi squared.
Is it x prime or x?
I put x prime equal to 0. So basically I took this
okay.
And I'm left with x over CT, which is just the velocity. So 1 minus tangent hyperbolicus of phi, right, is cosine hyperbolicus minus sine hyperbolicus divided by cosine hyperbolicus, all these squared, is just 1 over cosine hyperbolicus phi squared, right? And then sine hyperbolicus phi squared is just cosine hyperbolicus of phi squared minus 1. So from here, I can simply write down that cosine hyperbolicus of phi is just 1 minus tangent hyperbolicus of phi squared minus 1/2, which is 1 minus beta squared minus 1/2. So I call that gamma. And sine hyperbolicus squared just what did I do? Okay, well, this is just cosine hyperbolicus square minus 1. So you can just remove the square. Sine hyperbolicus of phi, right, is just gamma squared minus 1 for 1/2, which is just gamma beta. So with these new definitions of gamma and beta, then we simply have that CT prime, right, is just cosine, right, is just gamma times CT minus beta x. And x prime is just gamma times x minus beta CT. Right?
Asaf?
Yeah.
Why did you take x prime to 0 in the first place?
Why did I take x prime to 0? I just want to find the velocity at that point, right? For x prime, at the origin of coordinates.
Okay.
That's it. Now, does that ring a bell to you?
You mean you consider it as a reference frame, or?
No, I consider it as a Lorentz transformation between frame, the unprimed and the primed. Have you seen these equations before, guys? Have you?
Yeah, in first year.
Yes.
First year, right? You've seen this equation before. 10 minutes ago. It was the first time, I believe. Now, you believe me it's the same? Yeah. I'm not cheating. Okay, so this abstract notation that we just used, in fact, gives you exactly the same thing that you saw that you've seen in first year. Right? Only now you see the full structure. Right? Hey, you with me? Somehow I'm not seeing that many happy faces. Not sure why. Okay, let's move on. I have a few more minutes. Now, direct consequence of all that is this concept which is known as the time dilation. Any questions before I go on? Any questions, any comments? No? No. Okay, time dilation. Okay, I have a clock. Can you see my clock? Yeah. See, I have a clock. Okay, I carry the clock with me everywhere I go. Right now, I'm not going anywhere. I'm just sitting down. But everywhere I go, the clock goes with me. Right? That's clear. It's attached to my hand. Right now, I'm not going to take it away from my hand. Now, in my clock, in my frame, my personal frame, what is the separation, the spatial separation between two events, namely two ticks of the clock. So an event is when my clock is ticking. So tick, tick, every second it ticks. What is the spatial separation between two such events?
Zero.
Zero, because the clock is attached to me. I'm watching the clock as I go around. Okay, so I'm an observer, O, holds the clock. Now, two ticks of the clock are separated by delta x equal delta y equal delta z equal to 0. From my perspective. And the two ticks are separated by some time delta t, which we call it dt, right? dt is the nominal period between ticks as the manufacturer of the clock meant to, assuming that the clock is okay and is not having any trouble. Okay? Now, this dt, this is what the manufacturer meant. It has a name. You might know the name. How do we call this name?
Proper time.
So the proper time, that's right. This is the proper time. Very good. Right? It's often denoted as d tau. To denote it from any other frame, it's d tau. This is the time as measured in a frame in which the clock is not moving anywhere. It's just my frame. I don't see the clock moving. From my perspective, the clock is right here. Okay. Now, according to our definition of the interval, we have, now let's use the definition of the interval. Delta tau squared is just minus delta s squared divided by c squared. It's just minus 1 over c squared eta mu nu, delta x mu, delta x mu. Now, you are watching me. I'm moving now. You're watching my clock. You're seeing it moving. I'm moving relative to you. My clock is moving relative to you. Okay? So you're an observer O prime, right? And you see the same clock, which moves at velocity, let's call it V. So from your perspective, the two ticks, right? You have interval between the two ticks. They are separated by some time, delta t prime. Remember, you're the primed observer, right? So delta t prime and the space interval. What is the space interval? What is the space interval if you're seeing it moving at velocity v?
Vt.
V delta t? Right? So your proper time, delta tau prime, right? Just delta t prime squared minus delta x prime squared divided by c squared. 1/2. I just use that formula here. So it's just 1 minus beta squared half delta t prime. Delta tau is the proper time. It's defined using the interval. And the interval, remember, we all agree on the interval. So if we are both in the inertial coordinate system, let's assume for the time being that we are, right? Then the coordinate system are related via Lorentz transformation, right? And so delta S is conserved because the interval is conserved under Lorentz transformation. And so the proper time is invariant, right? So delta tau is equal to delta tau prime because the proper time is invariant. Right? So if you are seeing my clock in motion, right? So observer O prime that sees the clock in motion, right? Sees it ticking at period, right? Delta t prime is equal to what? What is delta t prime?
Delta tau over square root of 1 minus beta squared.
Very good. But what is delta tau? It's just my time, delta t. It's just gamma dt. So when you're seeing somebody is moving, the time that you're seeing it always slows down relative to if you're not moving, to a reference frame which is not moving. That's called time dilation. right? Okay, you're still with me? Okay. Okay, I think this is a good place to stop for now. We'll resume the discussion on Sunday. Any questions? Any comments?
Yes, I have a question.
Yeah.
It's about the previous example with the when you took x prime to be 0. I have another question about it.
Yeah.
If x prime is not 0,
yeah.
So can you also get the Lorentz transformation also?
Of course, but then you have to be careful because the one thing which you never want to do is to mix coordinates. You want to have two different observers. You want to have equations only for one observer, equation only for the other observer. This is, I want to use this opportunity to emphasize. This is something that students often tend to make mistakes on. Do not, under any circumstances, what happened? Do not mix coordinates. Decide which frame you're working. You can work in one frame or in the other frame and work in that frame. Okay? Don't mix coordinates because then you end up, I don't even know what you're doing. It's becoming completely meaningless. So yes, back to your question. Yeah, I could choose x prime, which is not 0, but it would just make my life miserable. So it's much easier to just take the origin of coordinates, put it to 0, and just do the demonstration there. The whole purpose here is to show you that this very abstract and mathematical notation that we were taking, mathematical path that we're taking, in fact, gives you exactly the same results that you've seen from first year. It's the same Lorentz transformation. We're just using now a new language. We're using all these indices. It looks like we're making our life much more miserable. We have to sum up big matrices with many terms, but you'll see that that makes perfect sense. It's mathematically well structured. The structure is very well defined. And this is what will enable us to generalize that when we start to discuss curved spaces, which are non-Minkowski spaces. Then we could easily generalize the discussion. Okay. So it's really to show you that this language that we're learning now is the same as what you've already seen from your first year, just different language. Any further questions or comments? No? None? Okay. Hope it was useful. Let's finish the recording. Stop sharing, I think. I can do a stop recording.